Hello friends, in the previous video we have seen various tests about convergence of an infinite series. Friends, we have seen comparison test of first kind, comparison test of second kind, limit form of a comparison test and D'Alembert's ratio test. Also, we have discussed about Cauchy's root test. Friends, in this video, we will discuss about Raabe's test of infinite series. I am here writing the statement of an Raabe's statement of a Raabe's test. Raabe's test. Raabe's test. If summation un is a positive term series, is a positive term series, such that limit of n into un divided by un plus 1 minus 1 as n tends to infinity equal to L, then the series number 1, first condition, converges if L greater than 1. Number 2, diverges if L less than 1, and as usual the test fails. This test is also fails for L equal to 1. We have seen that various tests of an infinite series fails when the limit L is equal to 1. Now let us see the proof of this series, Raabe's test, where we consider the first case first, where we take this L is greater than 1. L is greater than 1. Now friends, we choose epsilon such that L minus epsilon is greater than 1. We choose epsilon greater than 0 such that L minus epsilon, this is new number, let us call it alpha, and it is greater than 1. Now what is given? We have it is given that limit of this term, say limit of n into un divided by un plus 1 minus 1 equal to L. Now by definition we know that for each epsilon greater than 0 there exists a positive number, m such that the modulus term n into un divided by un plus 1 minus 1 minus L is less than epsilon. This is for all n greater than equal to m. Now using the modulus property, we write this term as L minus epsilon is less than n into un divided by un plus 1 minus 1 less than L plus epsilon. here you can see that we have chosen L minus epsilon equal to alpha, which is greater than 1. So, we consider the second part of this inequality, that is here n into un divided by un plus 1 minus 1 is greater than L minus epsilon. I am going to write here L minus epsilon as a alpha. So, here it is a n into un divided by un plus 1 minus 1 is greater than alpha. This is for all values of n greater than equal to m. Okay. Now, let us multiply this number by un. So, we get here n into un minus un plus 1 multiplying by un plus 1. It is greater than alpha into un plus 1. Okay. So, here n into un minus n into un plus 1 is greater than alpha into un plus 1. Now, we subtract here, you can see that here we have un plus 1 and here this term is an n. Now, for symmetry here n into un, here n into un plus 1th term. So, here we add or we subtract un plus 1 on both sides. Okay. We erase some part of this to get a space to write this term. This is equal to, you can see that here I am going to write that term n into un minus after n into un plus 1 minus un plus 1 subtracting is greater than alpha u into un plus 1 minus un plus 1. Now, here un plus 1 we can take common and again minus is common. So, this will be n into un minus n plus 1 into un plus 1 is greater than here un plus 1 alpha minus 1 into un plus 1. So, let us call this as a equation number 1. In the limit we have this is satisfied for all the values of n greater than equal to m. So, now here in equation 1 we put here n equal to m comma m plus 1 dash dash up to n minus 1. We are going to put these quantities. If we put in equation 1 here n equal to m, then we get here m into um minus m plus 1 into um plus 1 greater than alpha minus 1 into um plus 1. Okay. Now, put n equal to m plus 1. So, m plus 1 into um plus 1 minus here this term will be m plus 2 plus 2 greater than alpha minus 1 into plus 2. Similarly, let us put n equal to m plus 2. Here m plus 2 into m plus 2 minus m plus 3, addition of 1, here there is additional 1. So, plus 3 greater than alpha minus 1 into plus 3. Now, continuing this term, we put the last one n equal to n minus 1 and hence this will be n minus 1 into un minus 1 minus n into un is greater than alpha into un, here we get. Okay. Now these are these inequalities. Adding all these inequality, we add all these, adding all these. Okay. So if we add all these, you can see that here this m plus 1 and this m plus 1 will get cancelled, minus and plus. Next term, this u m plus 2 and this u m plus 2 will get cancelled. M plus 3 and um plus 3 again will get cancelled. Every term will get cancelled in the left, and we remain here m into minus n into un, and this will be greater than, in the right you can see that here alpha minus 1, alpha minus 1, alpha minus 1. We take alpha minus 1 as a common, alpha minus 1 into you can see that we have plus 1 plus plus 2 plus up to un. Okay. So, summation un. Friends, we know that Sn equal to u1 plus u2 plus um plus plus 1 plus un, and Sm equal to u1 plus u2 plus this um. If we subtract this Sn minus Sm, we get plus 1 plus plus 2 plus un, and all the remaining terms u1, u2 up to will be cancelled. Okay. And here you can see that this is into m, this is n into un, and here plus 1, plus 2, un. So, for this bracket term we can write Sn minus Sm. Okay. So, we write here Sn minus Sm. Then what here m into minus n into un is greater than alpha minus 1 into bracket Sn minus Sm. Now, from this we can see that here we take this alpha minus 1 to this side. Here we get Sn. Sn minus Sm is less than 1 divided by alpha minus 1 into you can see that here we have m into minus n into un is greater than Sn minus Sm. So, when we subtract this term from this is a greater. So, obviously this Sn minus Sm is less than 1 divided by alpha minus 1 into m into um. Now, transfer this term Sm to this side. Sn less than Sm plus m divided by alpha minus 1 into um. Friend, you can see that is a fixed term, alpha minus 1 is a fixed term, Sm is a fixed term, every term is a fixed term. And here Sn is smaller than this fixed term. This shows that this sequence Sn of partial sum is bounded above. This sum is bounded above. Here Sn is a monotonic positive term series, sequence of positive term series partial sequence of positive term series, so it is obviously an monotonic increasing sequence, and monotonic increasing sequence is a bounded, and hence sequence Sn is a convergent. Sequence Sn is a convergent. This shows that the series is a convergent. So the series is convergent when L is greater than 1. Now we see that the series is a divergent whenever L is less than 1. Again, to prove this, we consider the term L plus epsilon, which is greater term, L plus epsilon less than 1. Case second, we are proving the case second where L is less than 1. Now it is given that limit of n into un divided by un plus 1 minus 1 equal to L. So friend, for epsilon greater than 0, there exists a positive integer m such that mod of n into un divided by un plus 1 minus 1 is less than epsilon. This is for all n greater than equal to m. We can write this as a L minus epsilon is less than n into un divided by un plus 1 minus 1 less than L plus epsilon. Now we need that this L is less than 1. So here we take this L plus epsilon, we choose this epsilon such that L plus epsilon is less than 1. This is restriction to epsilon, so that this will be less than 1. Then what we get, n into un divided by un plus 1 minus 1 will automatically be less than 1. Now here n is in multiplication transferred to this side. So this gives us un divided by un plus 1 minus 1 is less than 1 by n. Again transferring this 1 to this side, so minus become plus, and we get here un divided by un plus 1 is less than 1 by n plus 1. So this is equal to n plus 1 divided by n. Now if we take Vn equal to 1 by n, then Vn plus 1 equal to 1 divided by n plus 1, and Vn divided by Vn plus 1 equal to n plus 1 divided by n. So this implies that un divided by un plus 1 is less than Vn divided by Vn plus 1. Now look at this series summation Vn. Summation Vn means summation 1 by n, and we know that this summation 1 by n is an divergent series. We can apply the comparison test by comparison test of the second kind. As this series is a divergent, summation un is also divergent. Summation un, so series summation un is a divergent by comparison test of second kind. Now here we have proved that convergence if L is greater than 1, divergence if L is less than 1, and we show that this test is fail if L is equal to 1. So to prove this, let us take counter examples of this where we consider our familiar series, that is 1 by n. You can see that here if we take un summation 1 by n, where un equal to 1 by n, then un plus 1 equal to 1 divided by n plus 1, and un divided by un plus 1. So So this will be n plus 1 divided by n plus 1 divided by n, and un divided by un plus 1 minus 1 equal to n plus 1 divided by n minus 1. This is equal to n plus 1 divided by this minus n divided by n get cancel, and we get 1 divided by n. Now here limit n tends to infinity, n into un divided by un plus 1 minus 1 equal to limit n tends to infinity, n into, we have this un term, that will be 1 by n. So 1 by n get cancel, and we get 1, limit of this 1 equal to 1. Now let us consider the another series, 1 divided by n into log of n whole square, log of n whole square. So we have un equal to 1 divided by n into log n whole square, un plus 1 equal to 1 divided by n plus 1 into log n plus 1 whole square, and un divided by un plus 1 equal to n plus 1 into log of n plus 1 whole square divided by n into log of n whole square. Now un divided by un plus 1 minus 1 equal to n plus 1 divided by n into log of n plus 1 divided by log of n whole square minus 1. Now friend, we write this as, this is equal to here dividing by n we get 1 into this one. So this will be log of n plus 1 divided by log n whole square, and plus 1 by n into log of n plus 1 divided by log n whole square, and this minus 1 we write this as minus 1. Now let me make some space. First I am erasing the statement of this. We are proving that this series is fails for L is equal to 1. Okay. Now let us take the limit of this, limit n tends to infinity of n into un divided by un plus 1 minus 1 equal to limit n tends to infinity n into, we have this term, log of n plus 1 divided by log n whole square plus here 1 divided by n into log of n plus 1 divided by log n whole square minus 1, this one. Okay. Now you can see that I am going to separate this. So this will be separating the limiting term. Here we write this as, this is equal to, you can see that this is equal to limit n tends to infinity n into log of n plus 1 divided by log n whole square minus 1 in the one bracket plus here this n and this n get cancel, and we get limit n tends to infinity this log of n plus 1 divided by log n whole square. Now in the limiting case you can see that limit of this is equal to 1, is equal to 1. Here we get limit of this is equal to 1, but here this one and this one get cancel, 1 minus 1 this will be 0, 0 plus this one, this is equal to 1. Now you can see that here summation 1 by n, summation 1 by n is a divergent series, whereas this summation 1 divided by n into log of n square is a convergent series. So the Raabe's test fails where to give a definite information at L is equal to 1. So likewise the another test, this test is also fails to give a definite information. Now let us prove one example how we can apply Raabe's test. Test the convergence, test for convergence, test for convergence, the series alpha by beta plus 1 plus alpha divided by 1 plus beta plus like this dash dash dash. Okay. Now let us prove this. Here we have un equal to you can see that this is u1, this is u2. So whenever we have 2, here we have 1 plus and next term 1 plus alpha, 2 plus alpha divided by 1 plus alpha 1 plus beta into 2 plus beta plus this is a u3. u3 whenever we have 3, here are 2 terms. Okay. Whenever we have 2 in the suffix, we have 1 term. Therefore whenever we have n in the suffix, we have n minus 1 term, and 1 plus alpha, 2 plus alpha up to n minus 1 plus alpha divided by 1 plus beta into 2 plus beta dash 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 n minus 1 plus beta. Then we can write un plus 1, this will be 1 plus alpha, 2 plus alpha, 2 plus alpha dash 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 n plus alpha divided by 1 plus beta, 2 plus beta dash dash n plus beta. Now let us calculate un plus 1 divided by un. So un term is 1 plus alpha, 2 plus alpha up to n minus 1 plus alpha, n plus alpha divided by similarly 1 plus beta, 2 plus beta, n minus 1 plus beta into n plus beta into, now reciprocal of un, 1 plus beta, 2 plus beta, n minus 1 plus beta divided by 1 plus alpha, 2 plus alpha dash dash n minus 1 plus alpha. You can see that n minus 1 plus alpha up to this all terms will be cancelled, and we get here n plus alpha divided by n plus beta. Now if we take the limit of this, let us take the limit of limit of un plus 1 divided by un equal to limit of n plus alpha divided by n plus beta, dividing numerator and denominator by n, we get limit of 1 plus alpha divided by n divided by 1 plus beta divided by n. In the limiting case, here alpha divided by n will be 0, beta divided by n will be 0, and we get here 1. So this shows that limit of this is equal to 1, means the ratio test here fails. Here ratio test fails, therefore we apply Raabe's test. Okay. Now let us take the limit n into un divided by un plus 1 minus 1 equal to limit n into, already we have this un divided by un plus 1, and that will be n plus beta divided by n plus alpha minus 1. this is equal to limit n into n plus beta minus n minus alpha divided by n plus alpha. N get cancel and we get here this is equal to limit n into beta minus alpha divided by n plus alpha. Now here taking n common from the denominator and this n will be cancelled, this one and this one, here n we are taking common from the denominator, so we get this n cancel and we get limit beta minus alpha divided by 1 plus alpha divided by n. Let us apply n tends to infinity, so this will be 0 and we get beta minus alpha. Now we know that whenever L is a greater than 1, by Raabe's test the series converges. Whenever the limit, what is the limit here? You can see that the limit is beta minus alpha. So when the by Raabe's test here, by Raabe's test, by a Raabe's test, when beta minus alpha is greater than 1, the series converges, that is transferring these two, beta is greater than 1 plus alpha. Whenever beta is a beta converges if beta is greater than 1 plus alpha, and diverges if beta is less than 1 plus alpha. Whenever beta is less than 1 plus alpha, by Raabe's test the series diverges. Now let us consider the case when beta equal to 1 plus alpha. When beta equal to 1 plus alpha, you can see that alpha divided by 1 plus alpha plus 1 plus alpha divided by 2 plus alpha plus 1 plus alpha into 2 plus alpha divided by here 2 plus alpha divided by 3 plus alpha plus like this. 2 plus alpha will get cancel and we get 1 plus alpha, and in the denominator 3 plus alpha, so this will be alpha divided by 1 plus alpha plus 1 plus alpha divided by 2 plus alpha plus 1 plus alpha divided by 3 plus alpha plus. So this is equal to summation 1 plus alpha divided by n plus alpha, and 1 plus alpha divided by n plus alpha, so this is similarly like 1 divided by n, and we know that this 1 divided by n is a divergent series. So for beta equal to 1 plus alpha, the series is divergent. Hence by Raabe's test the series is converges only for beta greater than 1 plus alpha and diverges for beta less than equal to 1 plus alpha. Now